So let's see this in practice. I talked about the sequence 1 over n. You already told me what the limit is. Let's prove that. So let's just do this as a practice for how you should write a limit proof. And we'll see this anatomy showing up. So, claim the limit as n goes to infinity of 1 over n is, yeah, but say it louder.
0.
Right, that limit ought to be 0. If you didn't pick up on that fact when you were taking like Calc 1 and Calc 2, then I don't know how you pass Calc 1 and Calc 2. Right, limit of 1 over n is 0. As n gets big, 1 over n gets small. That's like, in fact, a good enough argument if you're taking Calc 1 or Calc 2. Let's actually come up with a proof. So I need to prove a universally quantified statement. I need to prove this line up here. So the first thing I need to do is start with consider any epsilon bigger than 0. Now, I need to come up with a choice for big N. And this is an explicit function. I have a formula for it, so probably I can get a formula for big N. But you know what? Let's come up with the formula for big N by figuring out what it is that I need to be true. There's the thing I need to be true. So to come up with a choice for big N, there's what I need to be true. And I get to assume little n is bigger than big N. So let's try to take something like this. Solve for little n. Does that seem sane? Let's try to do that. Let's manipulate this and eventually solve for little n. What seems like simple like that? What do you get? And right now this is just scratch work, so.
1 over n is less than epsilon.
Yeah, the minus 0 doesn't matter because it's minus 0. The absolute value don't matter because n is a natural number.
Would you have to state why 1 over n, the absolute value of 1 over n is just 1 over n?
Maybe in the actual proof. Like, maybe write down a sentence to explain why that happens. Okay, cool. So we get 1 over n less than epsilon. I want to turn that into something of the form little n is bigger than big N. So keep on solving. What do you get when you solve that for little n?
Greater than 1 over epsilon.
Yeah. And I guess you said it in the opposite direction, but who cares? If your philosophy was cross-dividing, then I guess what you would get, or yeah, what you said is fine. Neato. So it looks like if I know that little n is bigger than 1 over epsilon, then I can like cross-divide, which I don't know, was it actually one of the homeworks that you proved that you could do something like that? Something like it anyway. Like you proved at some point that if little n is bigger than little m is bigger than 0, then 1 over m is bigger than 1 over n is bigger than 0. Yeah, yeah. I know you proved it because that's one of the ones that I got graded last night. And that's kind of like what's happening there. But as we progress further into the class, we're not going to worry about citing the right thing for elementary things about inequality. Let's start writing that down. So what seems like a good choice for big N then? What do I need little n to be bigger than? 1 over epsilon. So consider any epsilon bigger than 0. Now I choose n. This walk that I just did that I don't want to see in your proofs is let n be bigger than 1 over epsilon. That's something that I do need to see. Oh, let's see. This depends on the choice of epsilon. The exists a big N that comes after for all epsilon. So it's allowed to depend on epsilon. So that's okay. Now, I need to consider any little n bigger than big N. That's the same sentence as suppose that little n is bigger than big N, right? I just need some way of making clear I'm assuming little n is bigger than big N. Then, let's do some stuff with 1 over n minus 0, with the goal being 1 over n minus 0 is less than epsilon. And you know what? Let's just start here. 1 over n minus 0, absolute values around it. What did we do with that? Equal to, and maybe I'll leave like the intermediate steps 1 over n equals 1 over n, since n is bigger than 0. A natural number is bigger than 0, so I get to assume little n is bigger than 0. All right, what next? So the next was thinking about this. So let's see, since n is bigger than 1 over epsilon, what can you tell me about 1 over n? Yeah, but just say it louder. You said the right thing. I can kind of read lips.
1 over n is less than epsilon.
Yeah, perfect. No, not 1. 1 isn't what I want there. Thus, 1 over n minus 0 is less than epsilon. Is that exactly the conclusion that I want to see? Nice. So, maybe we'll summarize what we did. We considered any epsilon bigger than 0. So, for all epsilon bigger than 0, we came up with a choice of big N. In fact, it was explicit. There is some big N, and maybe I'll even put it in parentheses, namely n equal to 1 over epsilon, such that for all little n bigger than big N, I assume little n is bigger than big N, but that's all I assumed. Absolute value of 1 over n minus 0 is less than epsilon. Is that exactly the definition of some limiting statement? Yeah. In conclusion, maybe that should be capitalized and there should be a period. Maybe that should be capitalized. In conclusion, 1 over n converges to 0. A little Helmholtz box because the proof is done. That seem all right? Did that seem like way easier than you remember seeing claims like that in Calc 1 and Calc 2? I hope. Yeah, and that just speaks to the fact that you know some more mathematics than you did a few years ago. Right. So, let's carry on thinking about limits. We're going to do things significantly more sophisticated than proving an explicit sequence has an explicit limit. And let's just carry on with that. All right, so there was like some spaces for me to write the stuff that I did. So, does every sequence have a limit? I don't think so. Can you like come up by just maybe you're calling some sequences you know? Give me a sequence that doesn't have a limit, that doesn't get close to a single level.
Xn equals n.
Yeah, that one will do. Right, there's a sequence that does not converge. That one's not the one I'm about to study. Here's another one. Xn equal to negative 1 to the n. And maybe we'll pick which one we want to study in this next argument. Those are sequences that don't converge. A sequence that doesn't converge, I'll say it diverges. Definition, if there does not exist a number L such that x sub n converges to L, then we say that xn diverges. And I'll try in practice to like have parentheses around my things that are sequences just to set them off as sequences, but I'm not going to be 100% with that. So claim, let's let f of n be negative 1 to the n. Is that a reasonable way of declaring a sequence? Yeah, a sequence is just a function whose domain is the natural numbers. Then the sequence f of n diverges. And maybe I'll see how people feel. The argument will be pretty similar either way. Should I do negative 1 to the n? No, there's too much stuff already typeset. Let's prove that this negative 1 to the n diverges. And then maybe we'll think about how you would adapt this to show that f of n equal to n diverges. So it's really hard to prove a negative. So instead of proving a negative, let's proceed by contradiction so we get to assume a positive and then just prove something that we know can't happen happens. And we don't know what that something will be, but hopefully it'll be something that comes up. So let's proceed by contradiction. So that means I'm going to assume that f of n equals negative 1 to the n has a limit. I will call that limit L. Does that seem like a reasonable start to a proof by contradiction? Yeah, I want to prove that it doesn't converge. Let's assume it converges. That means it converges somewhere. Let's give it a name. So I now have assumed that f of n converges to L. That means I now know that for every choice of epsilon, there exists some threshold number, big N, which I'm writing here as big N of epsilon, and I'll say some words about what that notation should mean. So that if little n is bigger than big N of epsilon, then the absolute value of negative 1 to the n minus L is less than epsilon. That's the statement of convergence. What do you think I mean by that of epsilon?
And it's somehow based on epsilon.
Yeah, n is allowed to depend on epsilon. In the previous example, it was like 1 over epsilon. So that parentheses just has the job of saying, well, different epsilons may give different big N's. N is a function of epsilon. All right, so let's go. So that's now something that I just get to know. So I know that this statement is true for absolutely every choice of epsilon, right? So I could take a single choice of epsilon, and I would get a conclusion out of that. And let's just hope that that conclusion will be a contradiction. So let's try it. Give me a choice of epsilon. Just give me a positive number. Pick your favorite one. 7. So if you don't have the ability to erase what you write, you might want to hold off on putting a 7 in that space because it might not be good enough to give us a contradiction. Let's take epsilon equal to 7. It follows then that as soon as a number is bigger than big N, I get an inequality, right? Is there an, so this, this should be big N of epsilon. So in fact, big N of 7. Is that true? No matter how big big N is, can I find an even number and an odd number bigger than it? Yeah, I guess that's like a consequence of Archimedes' principle, right? I can find a number bigger than whatever this is, multiply it by 2 to get something even that's even bigger, multiply it by 2 and add 1 to get something odd. That might not be the most efficient way, but that's a way. Cool. So this odd number, little n, is bigger than big N of 7. So what can you tell me about absolute value of f of n minus L? So what's the whole point of this big N? There exists a big N of epsilon, so that as soon as little n is bigger than big N of epsilon, this difference is less than that same epsilon. So absolute value of f of n minus L is less than 7, because that's what we're using as epsilon right now. F of m minus L, similarly, what is it less than? 7. Now we're going to get into the nuts and bolts of like why this being -1 to the n matters. Yeah.
Why did we say that f was an even number and then? Oh, okay.
Yeah, so let's go for the like, is each statement true so far? We don't know why it's useful yet. We'll see why it's useful soon. Let's treat that sense. Is there an odd number n that's bigger than this threshold? Is there an even number that's also bigger than this threshold? So if that's true. I haven't told you why that's a good thing to do yet. Hopefully that'll come up in the next step. Maybe one way of thinking of it is -1 to the n, it like behaves differently from evens as opposed to odds. What's -1 to an even number? Cool. What's -1 to an odd number? Cool. That's why. So let's use that right now. Since little n is odd and little n is even, what's f of m? What's -1 to an even number? Yeah, -1 to the m equals 1. Similarly, what's f of n? Oh, neat. So let's rewrite this line right here. So that means f of n was -1. Absolute value of -1 minus L is less than 7, and absolute value of 1 minus L is less than 7. And I claim that this will result in a contradiction. And let's see that contradiction this way. Well, that's the same thing as absolute value of 1 plus L, right? Those two are the same? Yeah. And that's the type of thing that I wouldn't even require you to like justify in terms of absolute value properties. It's something you're allowed to know now. So let's use this to get a contradiction. And maybe we will get one, maybe we won't. Let's try to understand the difference between let's do this. So on the one hand, absolute value of 1 plus 1 is 2. Oh, yeah, sorry. On the other hand, that's the same thing as the absolute value of 1 plus L plus 1 minus L. So far that seems okay. Do I have something that says that 1 plus L isn't very big? Do I also have something that says 1 minus L isn't very big? Let's break this up using the triangle inequality so I can use that. So this will now be less than or equal to. Is the step correct? As in follows from the previous steps? Oh, neat. Do I have an upper bound on how big absolute value of 1 plus L is? What is that upper bound? Same thing there? Cool. So it looks like I conclude that 2 is less than 14. Is that a contradiction? So 7 wasn't good enough, but I could have put anything in place of 7. And the same argument would have gone through. What seems like a better choice than 7? Let's try a quarter. So this is why I said don't put something in that space yet if you can't erase, because now I'm going to do lots of erasing. So let's take epsilon to be another positive number, 1 over 4. Is 1 over 4 positive? Yeah, cool. Is there an odd number bigger than big N of 1 over 4? Yeah. big N of 1 over 4 is some big number. It could be 10 bajillion. But then 10 bajillion plus 1 is an odd number bigger than it. Similarly, there's an even number, big N of 1 over 4. Little n bigger than big N of 1 over 4. It follows then that that's less than 1 over 4, and this is less than 1 over 4. So far, so good. And now let's just keep on going through. Do those lines still walk? Cool. Does this line still walk? Change the 7s. I guess they're 1 over 4s now. So I conclude that 2 is less than 1/4 plus 1/4. I guess that's also known as 1/2. Is that a contradiction? And maybe we'll add the sentence that explains the contradiction. So 2 is less than 1/2. This is a contradiction. So there can exist no such L, and f of n equal to -1 to the n does not converge. Oh, cool. Does that seem like a proof now? So in general, what's the thing that this argument is trying to get across? So in this argument, we got to assume that a sequence converges to a number. So that means we assume something is true for every epsilon bigger than 0. So that means that any choice of epsilon gives us information. A lot of time when you know that a sequence converges, you'll be able to plug a particular positive number into the definition of the limit, to this definition, and get an inequality. In this case, we wanted a contradiction, and we got one by picking the right thing to plug into that inequality. Other times we'll prove a positive result instead of something that we know to be false. Yeah.
Do you generally want to pick a small epsilon, or is that just good as problem?
Yeah, so a big choice of epsilon, whatever big means, big and small are inherently slightly vague terms. A big choice of epsilon probably won't tell you much. So that defaulting to something pretty small, whatever pretty small should mean, is probably a reasonable choice. So you went to a quarter, and there's maybe a game you could play of it's nice to pick the biggest epsilon possible. Make your proof be as strong as possible. You don't want to make an overly strong assumption. Could you pick something slightly bigger for the epsilon in this problem? Yeah, what's the biggest thing you could have picked? 1 would also have walked. But this is still a proof. It doesn't matter that your epsilon wasn't optimally chosen in the context of this class. If you want to take the arguments and implement them into an algorithm, maybe picking optimal choices is more important. Yeah, in general, something pretty small is going to be the thing you plug in for epsilon, whatever that means in the context of the problem. And we'll see lots of examples of that next time when we prove some limit laws. But let's carry on. So what's left in this particular section? Yeah, good. Okay, only one thing left. I've been saying the limit of a sequence. That means that word "the" carries some weight. A sequence better not be able to have 5 limits. Let's prove that. So let's let xn be a sequence. Let's suppose xn converges to L and xn converges to k. What do you think I probably want to conclude given that setup? K and L are equal. I want to prove that a sequence has at most one limit. A sequence can't have 5 different limits. Well, let's try to use this. So, our proof is going to appeal to the theorem that you proved in the inequalities packet that I said was a super important property of inequalities. And I'm not going to have you look it up. I'll just remind you what it says. So 2.2.10 was the thing that said A is less than or equal to B if and only if A is less than B plus epsilon for all epsilon bigger than 0. Ooh, notice this has an epsilon in it. That has an epsilon in it. Maybe we can get those two epsilons to like communicate with each other. That's going to be basically the idea of this proof. So, by theorem 2.2.10, if we can show that the absolute value of k minus L is less than epsilon for every epsilon bigger than 0, then I'll know that k minus L is less than or equal to 0. Is that actually what 2.2.10 would say? Excellent. Well, can absolute values ever be like negative? So if I know that the absolute value of L minus k is less than or equal to 0, then really the absolute value is equal to 0? But if the absolute value of the difference is equal to 0, what does that mean? Oh, L minus k. I guess it doesn't matter what order you put it in, but I should be consistent. L minus k is equal to 0. And so, L is k, which is good. That's what I want. So it's nice when you're going to like do some logical trickery to change the thing you're going to prove to explain why that'll actually do the job. But now that we've explained that bit of logic, and rewritten this so it's actually readable, let's try to prove it. So I'm going to try to prove that that this absolute value is less than every positive number epsilon. So, what do we want to show? We want to show that for all epsilon bigger than 0, absolute value of L minus k is less than epsilon. Groovy. And I'll kind of draw a picture of this. There's this number L, there's this number k. Right now I don't know that they're equal. But there's what I want. I want that distance to be less than epsilon. So I'm going to like draw a picture to plot out how the proof will go. I want L and k to be close. What's something that I know is pretty close to L? Remember, L is supposed to be the limit of xn. So terms of xn should get close to L. So eventually I should be able to get this distance to be as close as I want by taking little n big enough. What's something that I should be able to get close to this number k? Also L? Again, by letting little n be big enough? Maybe there are two different big n's there. Oh, wait. So I want this edge to be less than epsilon. And like, this is literally a triangle now. So what distances do you think I want to have on these two edges to get that information? Well, 0 would be too close. How about epsilon over 2? Right, the triangle inequality says that any edge of a triangle is less than or equal to the sum of the other two edges. And like, it is the same with absolute value. So I think there's what I want. So we'll consider any epsilon bigger than 0. Xn converges to L. So I can run this definition with absolutely any choice of epsilon I want, any positive number I want. I think I'm going to run this with that positive number being half of epsilon. Is half of epsilon still positive? Cool. So there is some big N, such that if little n is bigger than big N, then absolute value of xn minus L is less than epsilon over 2. Does that feel sensible? Similarly, since xn goes to k, there's some other choice of big N. Might not be the same big N, so I'll call it big N prime. So that if little n is bigger than big N prime, then what do I get to conclude?
Absolute value of xn minus k is less than or equal to epsilon over 2.
Cool. So the strategy I'll follow now is I want L to be close to K. So there's the thing I want to be small. I know that L is close to xn and K is close to xn. So let's add and subtract xn. Do you agree that that's actually equal? I feel like I skipped some wads though. I'm going to set n double prime to be the max of those two previous big N's, which whenever you see two different choices of big N, probably you're going to take the maximum of them. I'm going to assume that little n is bigger than big N double prime, which means it's bigger than big N and bigger than big N prime. All right, so let's play this game. And I'm going to use the triangle inequality. What does the triangle inequality let me do to this? What is that less than or equal to by the triangle inequality? Split it into two. And I could do that however I wanted, but I think this is the sensible way. No, not L. Or maybe it looks like I'm also using like a property of absolute values to change the order of the thing. Maybe you would even want those to be xn minus instead of the other way around. But it's the same. I'm not going to get hung up on that. Oh, there's supposed to be way more in the step. Okay, cool. So, L minus xn, do I know that that's less than something? Epsilon over 2? Do I know this is less than something? Epsilon over 2. And maybe I'll put this since little n is bigger than big N, and little n is bigger than big N prime. And what's the point? What's epsilon over 2 plus epsilon over 2 equal to? Epsilon. All right. So we've now shown that absolute value of L plus K is less than epsilon for every choice of epsilon. Absolute value of L minus K is less than every positive number. So by theorem 2.2.10, we conclude that this difference is less than or equal to 0. Since absolute value can't be negative, that difference is equal to 0. And so L equals K, as we claimed. That feel all right? Nice. So, I guess I'm pretty close to time. This says that I have less than a minute left. There's just one last definition I'm going to write down, and maybe we'll even prove this at the start of next time. A sequence is said to diverge to infinity, or the limit is equal to infinity, or whatever else, if something happens. And I'm not going to write that down now. We'll start with that next time. The sequence that you told me, xn equal to n, it does diverge, but it diverges in a special way. If I were to ask you what's the limit of the sequence xn equal to n, what would you like? Tell me. As n goes to infinity, where does n go? To infinity. It's one of these questions that contain their answer. There's a particular meaning to that, so we'll have to prove it. So that's, I guess, where we'll start next time. Nice. And remember, I'm starting class on Friday with a pop quiz. So remember to be surprised.